So let's do an example of checking that we have the functions to form a general solution. We're going to consider the differential equation y double prime minus 9y equal to 0, given the functions y1 equal e to 3x and y2 equal e to minus 3x. We still haven't gone over how to find those functions, but assuming you had, this is how we would know that you've solved the full differential equation. So first of all, for the functions I'm given, these are functions that solve the ODE. So when I plug them in, they satisfy the ODE, or I could say that they are solutions. And we can go ahead and check that. For that y1 equals 3x, I'm going to have y1 prime equal 3e3x, and y1 double prime equal 3 times 3 is 9, e to 3x. And so if I wanted to plug that into my differential equation right here, what I'm going to get is y1 double prime minus 9y1 is just that 9 e to 3x right here for my y1 double prime, and then the regular minus 9 e to 3x from that y1. Maybe I'll do like some squiggly underlines and dotted underlines. And those two cancel out, so I just get 0, which is what I want my differential equation to be equal to. I can do the same with y2, e to minus 3x. So its first derivative is minus 3 e to minus 3x. And the second derivative is minus 3 times minus 3 is positive 9. So if I plug them in, I'm going to get y2 double prime minus 9y2 is, again, y2 double prime is 9 e to minus 3x. Minus 9y2 was just regular e to minus 3x. And those cancel out, giving me 0 again. So both of these functions are solutions to the differential equation. Now that I know that, I just need to check those two conditions to make sure they form a set that makes a general solution. So the second condition is always easier. I like to do it right away just so I don't forget to do it. So I have two functions. And my differential equation is a second order ODE. So I'm done. Just check the highest derivative and make sure you have that many functions to meet this condition. And then the harder one is that condition for linear independence. I'll go ahead and spoil it. They are linearly independent. But we have to go through the work to check that that's true. So I'm going to form that Wronskian. First, along the top row of the Wronskian, I write out my functions, so y1 and y2. And then I go down the Wronskian and take derivatives until I have a square. So I've got y1 prime, y2 prime, and I don't have to take any more derivatives because this is a square. It's 2 across, 2 down. And I took those derivatives up above, so we can just go ahead and fill in what y and its derivatives are. We had e to 3x and 3e to 3x for y1 and y1 prime. Or we had e to minus 3x and minus 3e to minus 3x for y2 and y2 prime. And then to evaluate the Wronskian, we compute this determinant. And determinant is going to be doing multiplication across the first diagonal and then subtracting multiplication across the opposite diagonal. The formula is like for A, B, C, D, it's AD minus BC. You may have seen that before. So for us, I'm going to multiply diagonally first. I've got e to 3x times minus 3e to minus 3x. And then I subtract, and always be super careful here that you distribute any negative signs as they happen, but I multiply the off diagonal. So I've got e to minus 3x times 3e to 3x. When I multiply e to 3x times e to minus 3x, I add the arguments of the exponent together. So that's e to 3x minus 3x, or e to 0. So this is actually minus 3e to 0 minus 3e to 0. E to 0 is 1, so that's just minus 3, or minus 6. And I could have stopped maybe like here, because really what I cared about was that my Wronskian is non-zero. It doesn't really matter what value it is as long as it's not 0. So y equal to c1 y1 plus c2 y2 is a general solution. C1 e to 3x plus C2 e to minus 3x, based on it satisfying those conditions that we set out. To say a little bit about other vocabulary that's going to be used here, and that I used a little bit as I introduced this section, but we say that this set of functions that form a general solution are going to be what's called a fundamental solution set that forms the general solution. And it's just going to be if those 3 conditions are met. Oops, no curly brackets needed here. So if they are all solutions to the ODE, and there are n functions for nth order, and they are linearly independent. And again, the way we check that is going to be with that condition that the Wronskian is non-zero. Then the general solution to the ODE that I marked by that star is y equals, I'm actually going to write this on another line, is y equals c1 y1 plus c2 y2 all the way down through cn yn. And I think the next thing can be its own video, so I'm going to go ahead and pause here and move on.